Hello. Okay, let's wait for 5 minutes if someone will join. Uh, it is a compensation session, so you must have already attended this session. It's a session that was to be held on 7th of March, but I missed this session, so I had to postpone this. Yes, it was on 7th of March. And we have one more session in the evening as well. Okay. Um, these are the questions from week four. In week four, we discussed about equivalent circuit and also how we can calculate gain and everything. But there were a lot of questions, so we missed a few questions. So we will start from those, and then we will proceed what we had to discuss for week five actually. So okay, let's wait for a few more minutes. If someone will join, then we are good to go. So okay, let's uh, let's begin. Second. Sorry. Okay. So this is a question we have to find what is called as a voltage gain. So remember, this is a circuit. What we will first step is to find the equivalent circuit, right? So let's draw the equivalent circuit. And what we do in the equivalent circuit? Always what we do is we short capacitor and ground the DC, right? One second. Okay, let's draw. CKT we write as a short form. It's not actually a short form, just for the purpose of writing it shortly. We write it as CKT. Okay. So this is your way in. Sorry. It's happening. I don't know. This is your way in. Short the capacitor. This is your R. This is your second resistor. Here to be ground. R1, R2, right? This becomes your VG. And this is your source. This becomes your GM VG. This is source, right? This is your RD, and this is your V out. Is it correct? Yes. Okay. This is to be VGS. This is VGS. So R1 is in parallel to R2, right? So, okay. So we have to find gain, right? That is V output by V in. Here V in will be equivalent to, here VGS will be equivalent to V in. Now look at this node. Let's say it is node A. We'll find KCL at node A. What will we write? V output divided by RD, right? Plus JM VGS equal to 0. right? So can we write it as V output is equivalent to minus Gm RD VGS, or V output by VGS as equal to minus Gm RD. So my gain, that is A, is a voltage gain, is equivalent to minus Gm RD. What does minus signify? Minus signifies that there is a 180-degree phase change. All right. Okay. So now that we have gain is RD given to us. RD is given to us as 2 kilo ohm. Now we have to find GM. Let's find GM here. So we know from MOSFET equation, is this a NMOS or PMOS? NMOS, right? ID is equivalent to K in saturation. If we write the equation for saturation, K W by L 2 times VGS minus VTHM whole square, right? Now, if we have to find GM, what we will do, DIDS by dVGS. GM is transconductance, output current by input voltage. So what we will get is kW by 2L into 2 VGS minus VTHL. Now kW by L is given to us as 1 milli, that is 10 to the power minus 3 into VGS minus 1 volt. Now what we have to do, we have to find VGS. VGS will be here, GS. So can we directly find VGS? Let me write here in this box. This is simple a voltage divider, right? Here between R1 and R2. So VGS will be equivalent to R2 divided by R1 plus R2 into VDD, right? That will be R1 is 60, R2 is 20 ohm. One second. R2 is 60 divided by 20, that will be 60K 60 divided by 80 into VDD is 2. Okay, 4, 2, 4, 3, 2, that is 9 volt, right? Can we cross check it? 2, 4, 3, right? So my GM will be 10 to the power minus 3 into 9 minus 1 is 8, that is 8 milli Siemens. So now that we have GM equal to 8 millisiemens, now we can find gain, that is voltage gain as minus times 8 milli into 2k. K in milli will go, that will be minus 60. Let's see if there is an option. No, somewhere we did wrong. Let's cross check. Okay, okay, here. It is R2. R2 is 20, 20, sorry. R2 is 20. This is 80. 4, 3. Hmm, 20 will go. This is 3 volt. This should be 3 minus 1. That is 1 second. 2 milli. Right, let me clear this as well. So it is 2 millisiemens. So my gain is minus. So let's just minus GMRD, that will be equal to minus 2 milli into 2K. Okay, this will go, that is minus 4. Here, it's since it is actually a minus 4 gain, but it's a mod of minus 4. So yes, this is the correct option. So this is how you find small signal voltage gain. We had to recap as well how to draw the equivalent circuit. We consider capacitors to be short at the input frequency. If a frequency is given, let's say that it is said that at these frequencies capacitors are not short, then you have to consider that. But if it's not given, then you should consider them as a short, and you have to ground to DC. Since this is a small signal voltage gain, that's AC gain. Okay, let's see what's next. Now, now the question says, find the input resistance for the circuit shown in figure this. You have to find input resistance. Okay. Assuming signal coupling capacitors are shorted. Your coupling capacitors. Coupling capacitors, why are they called as coupling capacitors? Just for allow if you want to only have DC signal or AC signal. Let's say, for example, in this circuit, this will not allow DC to flow through here. It will only allow AC to pass. Similarly, it will allow AC to pass here and no DC current. So this is for that biasing purpose and to differentiate the path between DC and AC. One second. Okay. So now you have to consider this short. Let's draw again. We have to draw equivalence. One second. Hello. Hello, Bonish. We are doing the previous week assignments. I suppose you have already uh, attended the session. Have you done this question, or I should repeat what I was mentioning till now?
No, sir, I have not it.
Hmm? You're not audible. Hello.
I have not done, sir.
You had not done?
Yeah.
So you want me to repeat what I was mentioned?
No, no need to repeat, sir. I will see in the videos, recorded session.
Okay,
No need.
okay.
You can proceed
So
further.
let me just mention that these are the week four questions. You have done week four. There were some questions which were not shown. So this is related to MOSFET and small signal voltage gain. Mm, so this was the same question I have shown here. So now next is to find input resistance for the same circuit. So first step is again draw equivalent circuit, right? So one second. So this is the circuit. We had to draw equivalent circuit of it. So we short the capacitor obviously. This is S. So this is VGS, right? So I have not uh, written V in. I will just say that for to calculate the input resistance, what we do is that we use test source Vx with current known to us as Ix. So to find resistance, we can use directly Ohm's law. We will get Ix into R, right? R is our in. So I will use a test source here, Vx, and current Ix flows. So what I will get is I will get is I will get my Rn. So let's see. Uh, okay. So if I apply a Vx here, if I apply Vx here, and also I think I should connect it to. No, it's okay. So if I connect a Vx and Ix here, so we only have one path, that is this one. So we will get Vx equivalent to Ix R1 parallel R2. So my input resistance can be simply written as Vx by Ix, that is R1 parallel R2, right? My R1 R2 is R1 is 60k and it is 20k. So this is input will be equivalent to 60k into 20k divided by 60k plus 20, right? That is 60k into 20k divided by 80k. It gives me 15k, right? So this is how you find resistance in a circuit. You apply We apply a test source and simply follow the Ohm's law and calculate it. All right. So let's see what's the next. Next is to find the output resistance of the circuit. Again, what we will do, short short input source, voltage source, short capacitors. That is why I have to again draw the equivalent circuit. So this will be ground here, and this will be R1 parallel R2 here. You should also try that whenever you do these questions, you draw the equivalent circuit as well. So it will help you. And if you sometime get complex circuits, it will be easy for you to draw the equivalent circuit. So now what we will do is that we will connect Vx, Ix here. So let's see first. It is 0 volt here. So my Vg will be 0. This is also grounded. So my VGS is 0. So I can ignore this part easily. And these are decoupled. So and this will also be equivalent to 0. I am only left with RD, and this is my Ix, this is Vx. So my Vx is equivalent to Ix into RD. So my output resistance is simply Vx by Ix, that is RD. So the value of RD was 2 kilo ohm. So my output resistance is simply equal to 2 kilo ohm. Okay, fine. So this is how you find output resistance. It's simple. Next is find the value of signal coupling capacitor C1 such that the lower cutoff frequency of the amplifier shown in the figure 4.3 is 10 Hertz. So we have to find C1. What is the value of C1? And such that mm, cutoff frequency, let's say FT is 10 Hertz. That means after this frequency, this will start acting as a short. Give it a try. I'll wait for 2-3 minutes. Okay, let's do it. All right. So we had to find the value of coupling capacitor C1. So is that so, okay? So what we'll do is that we'll find gain. Okay, gain in terms of VGS is equivalent to V output will be V output by VGS can be simply written as minus GM RT. We derived this earlier, right? So my V output is simply minus GM RT VGS. But what is VGS here? It's not simply V in, right? VGS will be simply equal to R1 parallel R2 divided by R1 parallel R2 plus XC1 into V input. So my V output by V input equivalent to minus GM RD divided by, sorry, multiplied by multiplied by R1 parallel R2 divided by R1 parallel R2 plus XC1. This is how you will obtain gain. Now we know if I divide this by R1 parallel R2, we will get divided by 1 plus XC1 by R1 parallel R2. XC1 is simply equal to 1 by j omega C1. Alright, so what we need is this XC1 or oh, 1 second, or we could have written it uh, in this way minus GM RD divided by 1 plus 1 by j omega C1 R1 parallel. Or if I multiply and divide it by the, we will get j omega C1. So my pole actually, my pole will be at omega C1 R1 parallel R2 equivalent to 1. This is a condition for cutoff frequency. Okay, now we will get C1 as 1 divided by omega times R1 parallel R2. Now what is R1 parallel R2? That is 60k into 20k divided by 80k we actually calculated it, it comes out to be 15K. So my C1 is 1 divided by 2 pi ft into 15K. Ft is given to us as 10 hertz, right? So C1 is K will go 10 is power minus 3 divided by 2 pi into 10. So if you calculate it, it will come out to be 1 microfarad. Let me still use the calculator again. Divided by 2, divided by 3.10. Point. Okay, and 15 as well. Yes, it comes out to be 1 microfarad. So this is how you find the cutoff frequency of the amplifier. Another approach would be simple. You just look at the capacitor, okay, then find R equivalent. What we'll do is you ground these things, alright, and you ground here as well. Then you just look what is the total resistance. If there was a resistance here, that will get directly added to this. So R equivalent is simply R1 parallel R2. Then time constant will be simply equivalent to omega. No, sorry. Then you can directly write it as omega C1 R equivalent is greater than 1. This is also an approach where, from which you can get the values. Okay, so this is done. Okay, this is I think the last question from the previous week. So let's see what does it say. You have to find power dissipation of the amplifier. What is power dissipation? You have voltage applied, then you have current flowing, so there is always a loss, right? How can you calculate it? By using directly a formula V into I. So now here for the circuit, okay, look at circuit. One second. If you see the circuit, there are two paths. There are two. There are two paths. One this one. This is normal transistor path, and this is biasing circuit path. So there will be dissipation, power dissipation through these two. So we have P1. We have to calculate both losses, right? Both power dissipation. So my power will be P1 plus P2. P1 will be simply equal to bias voltage into transistor current and my P2 will be equivalent to bias voltage into bias current, right? So let's first calculate IDS. IDS is given by the formula VGS. We already calculated, it comes out to be 3 volt. In case it's given by milli, the 3 minus 1 is 2 square. So I current is 2 milliampere, right? So my P1 will be equal to VDD is 12 volt into 2 milliampere. That is 24 millivolt. This is one. Next is we have to calculate I bias. So you have this R1 and you have this let's forget about what is from the side. This is 12 volt. This is so this is 3 volt, right? So I can directly write I bias as VDD minus VGS divided by R1. That is 12 minus 3 divided by R1 is I think 60K. So that is 9 divided by 60K comes out to be okay. It comes out to be, let's keep it less. Hmm, sorry. Okay. So my power will be equal to VDD into I bias. That is 12 into, that is 1.8 volts. So total power dissipation will be equal to P1 plus P2. As I said, that will be 24 millivolt plus 1.8 millivolt. Total is 25.8 millivolt. Right. So this is how you find the power dissipation in the circuit. Okay. Now, now that we have completed the part of week 4, now let's move on to what we studied in week 5. In week 5, you have lectures on how you can find, again, it's about the frequency response of the circuit. So when you have to find the frequency response of the circuit, you should know Laplace transform as well. As well, you should have a good hold on how to draw the equivalent circuit. Equivalent circuit is important here. Okay, so let's just go on. I hope you have gone through the lectures. Now we will just directly start with the questions, I suppose. Just just simple. I want to first draw one equivalent circuit here for a simple. transistor. So this is, let's say, V in. So this will be my V in. This will be my RS. This will be my R pi. Let's say there is, let's say there is some output resistance, load resistance, RC, and some load capacitance, CL. Okay, so now what is C pi? C pi is capacitor from base to emitter, and we have another one that is a coupling capacitor between your base and collector. So this is a normal equivalent circuit for BJT. So you should know this equivalent circuit because it's important for all the questions we are going to do. So the question says that C pi and C mu are negligible. So what we can do is that we can ignore these capacitors in our analysis because they won't act as a short at any frequency. So for the question as here, let me just check. So it says that we have these parameters. Okay, let me just underline these. So there is nothing given about CPAN. In question it says that assuming parasitic capacitance are negligible. So we can just ignore them. And if I had to draw the equivalent circuit for this one, I will write here. I'm not ignoring capacitances here because we have to find the cutoff frequency. So when you have to find the cutoff frequencies, you should draw the equivalent circuit with capacitors as well. This is our problem. R2. This is my R pi, right? This is RE. This is CE. Okay, this is getting jumbled here. Let's draw properly. Okay. Okay, so this is our equivalent circuit for the figure 5.1. So just remember that lower cutoff frequency will be given by your input part. So how do you find it? So remember that if you want to find a time constant or cutoff frequencies related to a particular capacitor. So what will you do is that you keep that capacitor and short every other capacitor in the circuit, in the equivalent circuit. So as I said, for input cutoff frequency, low frequency cutoff, lower cutoff frequency that will be related to input part. So we will take C1 capacitor, we'll take C1 capacitor and short every other. Okay, so let's draw the equivalent circuit. I have drawn it. I will just directly write how it looks. To okay, this is how it will look for C1. 1 second. Okay. Now, to find the time constant, we need to first find the equivalent resistance. Equivalent resistance that will be given by your Rs, your Rs plus Rin. Now, if we have to find Rin, we can directly see that Rin is equivalent to R1 parallel R2 parallel R pi, right? So first we need to find R pi. Uh, do you remember the formula for R pi? No. R pi is, as we know, given by Vt by Ib, right? Hmm. So first, then we need to find Ib, right? Why I have chose R equivalent? Then omega R equivalent C1 should be greater than equal to 1, and this will help us find the lower cutoff frequency. So let's see We have to find IB first. Oh, let's draw the DC equivalent circuit. That will be voltage divider. Sorry. Right? This is correct. So let's apply a KVL through this region because VBE on is given to us. So how will it look like? VCC, let's say this is a voltage drop of VR1, we get VCC minus VR1 minus VBE on minus IERE equivalent to 0, right? So can we find VR1? Yes, VR1 is simply equivalent to R1 divided by R1 plus R2 into VCC. That comes out to be R1 is given as 8.4, R2 is given as 3.6, so comes out to be 8.4K divided by 12K into 12. So we R1 is 8.4K. Yes. So it comes out to be 8.4 volt. So we can then write as 12 minus 8.4 minus zero point 0.6 is equal to IE RE. That is 12 minus zero point 0.4 minus that is 9 divided by RE. RE is equivalent to 2K. That is IE. Therefore, IE is equivalent to 1.5 milliampere. Okay. Now we have to find IB, right? We know IE is equivalent to IC plus IB, right? So can I write? Is this correct? Yes, because beta is IC by IB. So my IB will be equal to IE divided by beta plus 1. That is 1.5 into 10 to the power minus 3 divided by beta is given to us as 200. So this is 201. It's going to come out to be 1.5 divided by 201. Sorry, that is 0.0075. IB comes out to be 0.0075 into 10 to the power minus 3. That is 7.5 micro ampere, right? Correct. Now what next? R pi. R pi is VT by IB, right? So this is 26 into 10 to the power minus 3 divided by 7.5 into 10 to the power minus 6. So it will be 26 into 10 to the power 3 divided by 7.5. So it is 26 divided by 7.5. That is approximately 3 point. It is 46. Let's say it is 3.5 kilo. So R pi is approximately 3.5 kilo. Next is now this R pi is in parallel to R1 parallel R2. One second. So we found R pi. Now it is, oh, sorry. Hmm. So we have to find R1 parallel R2 now. Let's see what R1 parallel. R1 is given to us as 8.4. I think we found it already. R1 parallel R2. No, this is 8.4K into 3.6K divided by 8.4K plus 3. Okay, this is 8.4K into 3.6K by 12K. 1K and 1K will go. Let's just calculate. Comes out to be 2.5K. Okay, so now we have R1 parallel R2 and now we can find R in. That will be given by 2.52K multiplied by 3.5K divided by 2.52K plus 3.5K. Okay, so let me just calculate it. This 8.82K divided by 8.5. That's 6.02K. It comes out to be 8.82 divided by 6.02. It's approximately 1.45K. Okay, so this is R in. Now R equivalent is, as I said, RS plus R in. So RS is given to us as 80 ohm plus this is 1.45K. So this will be plus 1.45, 1.53K. Okay, so now we have our equivalent. So therefore, we have omega C1 R equivalent greater than 1. This will be give me Ft should be greater than 1 divided by, try to find, okay, frequency, 2 pi C1 R equivalent. So my lower cutoff frequency will be equivalent to 1 divided by 2 pi into C. What is C? C1. C1 is 10 microfarad. So Ft will be equal to 1 divided by 2 pi into 10 microfarad into our equivalent, that is 1.53 10 is power 3. So that is equivalent to 10 is power 3 divided by 2 pi into 10 into 1.53. Let me just calculate it. 1000 divided by 2, 3.14 divided by 10 divided by, comes out to be, comes out to be 10.4 hertz. So yes, here. So this is the correct answer. So this is how you find the cutoff frequency for a particular capacitor. Because if this is a capacitor, this is a RC, this is a resistor, so this will find a RC network. So every capacitor has some time constant associated with it. So this is one approach. So just to look back at it, so you find first the equivalent circuit, then you short every other capacitor and find the equivalent resistance, and that will help you to find the cutoff frequency by using this formula. So this is all right. Let's move on to the next question. Okay, now we have to find upper cutoff frequency. Again, these are given as negligible, so we will focus on first on the output part to find the upper cutoff frequency. Okay, again let's draw the equivalent circuit for load capacitor CL. So that will be right. This is R in. This will be now. If we look at here, this is zero, so this will also be zero. That will be it will be open. So we only have this part. So my resistance is RC and my capacitance is CL. So I can directly write omega RC CL greater than 1. One second. Okay, so we have to find upper cutoff frequency. Let's say this is upper cutoff frequency. We'll get equivalent to 2 pi CL into RC. RC is given, right? C is given to us as 4 kilo ohm. So I will write it as 1 divided by 2 pi into CL also is given to us as 100 picofarad. And 100 into 10 to the power minus 12 into 4k. 1 into will go, and we'll have 10 is power minus 10 minus 3, 10 is power minus 7, 10 for 7 divided by 2 pi into 4. Okay, so let me just calculate it. 1 divided by 2 divided by 4 divided by 4 comes out to be, sorry, I'm new to this, so it comes out to be point 0.0398 for 7 hertz. That will be, let's see what are our options first. Here 98 kilohertz is one option. So yes, so if I simplify this, I will get 398 kilohertz. Is that right? Okay, so it's exactly the correct one. So this is your upper cutoff frequency. So this is how you can find the values. Okay, let's move on. Now we have to find gain. Okay, for gain, remember that if a given frequency is above lower cutoff, then you should then we have to find gain as we normally do. Let's see. Given omega is 200 kiloradian per second, so that means 2 pi f is 200 kiloradian per second. So my f is 200 into 10 to the power 3 divided by 2 pi. That is 100 divided by 3.14. That is 3.31.8 kilohertz. 1 second. And my lower cutoff frequency was 10 hertz. So I can proceed and find the gain as simply V output by V in, or it's called as a mid frequency gain. So let's see my equivalent circuit. All right. So mm, my output by V in dash will be simply given by GMRC. And we know this is Rin. Rin is given to us as Rin. Let me just check the calculated Rin in previous step. 1.45K. Rin is 1.45K. So my V in dash will be equivalent to Rn divided by Rn plus Rs. That is 1.45K divided by 1.45K plus 80 ohm. We can write 80 ohm as 0.08K, and it will give me the in dash will be equal to 1.45K divided by 1.53K into V in. That is 1.45 divided by 1.53, 0.94. V in dash will be equal to 0.95, approximately 0.95 V in. So my gain is mm, 0.95. This is mod 0.95 GM RC. So first we need to find GM, right? So my GM is IC by VT, right? We know IE is equal to IC plus IB. IE we calculated as 1.5 milliampere. So we can just approximate IC is nearly equal to IE is equal to 1.5 milliampere because IB is very less. So my GM is simply 1.5 milliampere divided by 26 millivolt, right? That comes out to be 1.5 divided by 26. That is 0.057 Siemens, right? So now gain will be 0.95 into 0.057 into RC. What is the value of RC? RC is 4 kilo ohm. 4 kilo ohm. So let's just calculate. 4 into 0.057 into 0.95 into, comes out to be around 460. Let's see if there is an option. Oh, I mistook something. One second. 230 seems close option. Mm, okay, let me just cross check what we did. Okay, so V in dash is equivalent to 0.95 divided by 0.9. Okay. Um, if I don't do any attenuation, I'm getting 228. second point and 5 into 5, 7. Okay, let's keep it as it is. So this is how you solve it. Okay, maybe there is some mistake somewhere, so you can look for that. So this is for time being. This is our gain. Obviously, this is negative. So this was for this question, how you find a gain. I suppose it's the correct option is this one. So please check this again if I have done somewhere mistake, so you can correct it. Okay, now we have to find the effective input capacitance seen looking into the base of the terminal. So here we are given C pi as 12 picofarad and C mu as 6 picofarad. So before we jump to this, first we need to know Miller theorem. What does Miller theorem say? Miller theorem say if you have a capacitance or any impedance connecting input port and output, you can always decouple by using this theorem. So if this is my V1, this is AV, this is V2, and this is Z. So you can always decouple them and we can write it as Z1 and Z2, where Z1 is given as Z times 1 by 1 minus AV, and Z2 is given as AZ times AV minus 1. And if it is capacitance, then like this, for example, CF, then it can be written as input. C input is equivalent to CF1 minus AV, and C out is equal to CF1 minus 1 by AV. So this is the how you write the Miller theorem variables. So how do we get it? Just a brief introduction how we can obtain these values. Let's say you have this network, this is V1, this is V2, and you have this impedance connecting input output. So let's say this is current I, this is current I2, this is current I1. So if we write KCL at this node, what we will get? I is equal to I1 plus I2. Let's say total impedance is Z in, and here it's R in, and here it is Z given to us. So I will be equivalent to V1 divided by Z in divided by I1 is simply equal to V1 divided by R in, plus I2 is V1 minus V2 by Z. And we know V2 is equivalent to amplified signal of V1. So can we write it as V1 by Z1 in plus V in by R in plus V1, that is V1 times 1 minus AV by Z. That's right. Or in more simplified form, if I divide it by, sorry, this is V1, yeah, okay. If I divide both sides by V1, I will get 1 by Z in is equal to 1 by R in plus 1 divided by, let's say I write it in this form. So this is our form. Can I treat it as an equivalent, or let me first write it as Zn is equal to 1 by Rn plus 1 by Z Miller input. And here, this is a parallel combination of Rn and Zn. So that means I can write at the input port another impedance, which is like this, Zn. So my Z min is given by Z divided by 1 minus AV. That is what we wrote here. So similarly, we can apply the KVL at node 2, find this as I1 and I2, and you can get this second equation. Now if Z is capacitance, then Z will be equivalent to 1 by omega C. So it will be, it will just be a reciprocal. That will give me, let's say omega omega, and we cancel that. We'll say M in will be equal to C 1 minus AB plus CM in will be equal to C times 1 minus A. So this is how you get this formula. Okay, all good. So for this question, we have to find effective input capacitance, right? So we have the equivalent circuit. Let me just write this. This is C pi. C1 here. And this is C mu here. So you have to apply Miller theorem on C mu. Therefore, your total input capacitance will be then, when you apply the Miller theorem on C mu, you will get the capacitance here, C mu dash. And then your total input capacitance will be C pi plus C mu dash. And C mu dash can be now given by as the Miller theorem, that will be given by C mu times 1 minus AV. What is AV? You know now what is AV, right? We already calculated that is GMRC. AV is given by minus G times RC. My GM is 0.057 into RC is 4K. So it will be around 0.057 into 4 into 228. So now C input is equivalent to C pi. C pi is given now. It is C pi is given to us 12 microfarad, 12 picofarad. That is 12 picofarad plus C mu is given to us as that is 1 minus minus plus 228. So we solve this. What we'll get is 228 multiply plus 1 into 6 plus. Yeah. So it comes out around 1386 picofarad. Okay, so this one is the nearest. So there is again some calculation, maybe GM is not properly calculated. So you just have to find the correct value, and this one is the correct answer. So what we studied here is a mellotherm, how to decouple the two into input and output. It makes the solving the question easier. And for the capacitance, these are the formulas. Please do remember these formulas. This will help you with the solving the questions. Okay, and here we apply the Miller theorem for this capacitance, that is CBC, and we will have its one component here as well. So it's okay. Okay, now we have the last question for today, I suppose. Yes, we have to find upper cutoff frequency, upper cutoff frequency of the amplifier, and when we have C pi and C mu 6 picofarad given. What we'll do is first is find the total input capacitance. That we already did is the correct answer was 1403 picofarad. Okay, so to directly answer the things we can get is lower cutoff frequency. Lower cutoff is given by omega r. I think it was 1 second. Omega r equivalent C1. Omega r equivalent C1 gave you a lower cutoff frequency. Now to find the upper cutoff frequency, what we have to do is we keep C in and short every other capacitor, so we'll get it like that, like this. So I suppose 1 second. And now here we have another capacitor. Huh. So C1, we have another capacitor now here, C input. So this will be in parallel to. Mhm. Yes. Let's just. I think it will be given by Rs plus Rn C input omega is equal to 1. So let's just calculate. It comes out to be 1.53 K. C input is 1403 into 10 to the power minus 12. 2 pi f is equal to 1. So f will be equivalent to 10 to the power 12 divided by 2 pi into 1.53 into 10 to the power 3 into 1403. So let me just show it. 2 divided by 0.1 megahertz. Okay, so this is on the higher side, and we similarly we can find the output part. Output capacitance will be simply equivalent to using the formula second one on this one. C output is called 1 minus 1 by AV. So this will be equivalent to 6 picofarad. 1 plus 1 by 200. What was the K? 230. 30. So this is nearly equal to 6 picofarad. So this will be in parallel to your output capacitance, that is CL. So C output is equal to CL plus C out. That is equivalent to, let's say, CL. CL is equivalent to, I have the values. CL CL is 100 picofarad, so this will be a total of 100 picofarad, say 106 picofarad. So cutoff frequency will be omega RC C total output into 1. That will give me F is equal to 1 divided by 2 pi RC is 4K into 106 picofarad. That comes out to be 10 raised power 12 divided by 2 into 3.14 into 4 into 10 raised power 3 into 106 divided by 2 divided by 3.14 divided by 4 divided by comes out to be nearly equivalent to 380 kilohertz. Hmm. So this is very near to this option. Yes. So this one should be the correct option. So this is how you find. So this will be your upper cutoff frequency because this is very high value than this one. So their output cutoff frequency will be determined by your output capacitance, load capacitance. So okay, so this is for the morning session. We will continue. There are a few more questions on the same topic that will be based on MOSFET. We will continue in the afternoon at 6 p.m. And this recording will be shared, so please check the recording.